So we now have a nice easy way to estimate E of theta. So we said E of theta we can get just by doing a simple tracer experiment. We measure at the exit point the concentration as it varies with time, and we can just divide that by the area under that curve. So that's how we get E of theta. And of course we also want the internal age distribution I of theta. And what we'll try to do now is estimate that from a mass balance. So let's consider the basic mass balance, where we ask ourselves how much of fluid elements of a specific age range are inside that reactor, given that we've lost so many exiting and given that we've gained a certain number initially. So a useful thing along the way is going to be a function that we'll define here, which we'll call f of theta. So f of theta is the cumulative integral for E of theta. So let's just make it theta dashed to just to be different from this theta here. So we are creating this definition, we are creating this function f of theta like so. And the physical meaning of this is that this is the fraction of fluid elements of age at most theta at the exit point. So fraction of fluid elements at the exit of age at most theta. Right, so just looking at how we computed that, you can see here E of theta, we know E of theta is a function such that if you integrate over it, you get the fraction of fluid elements of that age range. So here we are integrating from naught to theta. So from the absolute minimum possible age to this specific age theta, which is the argument of this function. So this is the fraction of fluid elements of age at most theta. So everything up till age theta, that's f of theta. Now let's try and do the mass balance on fluid elements of age theta to theta plus delta theta. So we are looking for the fraction of fluid elements inside the reactor in that age range. So we know I of theta delta theta is the fraction of fluid elements in age range theta to theta plus delta theta. And if we multiply this by the volume, then this is the volume of fluid elements in there in that age range. Now, how many fluid elements did we gain in the first place? Right, that's a question that we can ask. We know we are looking at these fluid elements that are currently in the reactor of that age range, right? We're often saying that age range, so theta plus delta theta. So that's the age range of interest, and we got to that age by fluid elements entering here at some point. So obviously those fluid elements that are in there of age theta now, they entered theta time units ago, and when they entered, we are asking how much entered in the first place. So if we think about it, we are gaining fluid elements here from the entry stream, and we've got a volumetric flow rate there, which we are calling Q. So the volumetric flow rate here equals the volumetric flow rate there. So that's Q, and that's flow rate. This is an actual volume. So we want to convert this volumetric flow rate to the volume. And let's think about it. If that's our flow rate, and we are interested in this specific time range, then how much of what volume of this entered in the first place? So if you look at this range, you'll see that this has a if you like, a width. The width of this age range is delta theta. So it took delta theta time units for this group to enter in the first place. So if, for instance, we were asking fluid elements that were there for 10 seconds to 20 seconds, right, then those fluid elements entered over a 10-second interval. Well, actually, let's make it 30 seconds to 40 seconds, just so that 10 doesn't recur. So 30 seconds to 40 seconds. So if we are interested in fluid elements that were there 30 seconds to 40 seconds, then it took 10 seconds for that group to enter, right? So it took delta theta time units for this range of fluid elements to enter in the first place. So if we say here Q delta theta, then this must be the original volume of fluid elements that entered, right? So it's fluid elements are entering continuously, and if we take the time, if we take a specific time range, then that must be the volume that entered. So that's what we had originally. That's where this range came in. And actually this is independent of the specific range. The theta value here doesn't really matter. So any range, as long as it has a width of delta theta time units, then that's going to be the total amount of stuff in that subgroup. So we have a certain amount left over. This is the volume that's still in the reactor, and that's a result of this volume entering in the first place. Now we can, to complete the equation, we need to write down how much did we lose over time. So we've lost a certain volume due to the exit stream. And you see here, we can ask, what is the total volume that exited over the lifespan of this group? Right, so there's a group theta to theta plus delta theta, and we lost fluid elements from this original group. So we know this was the total amount in the group originally. So if nothing had exited over time, then this would be the volume that would be there. But we've lost a certain fraction of that. And you see we've already introduced this convenient definition. We've stated f of theta is the fraction of fluid elements at the exit of age at most theta. So this is the fraction that has exited the reactor. So we could say this is f of theta, and so we have an equation now that tells us the total amount that we would have had in the first place in this age range, and then we have also the fraction of that amount, the fraction of that amount that exited, and then if we multiply it with the actual amount, then that's the volume that we've lost from that original amount there. So you can see a couple of simplifications being possible. So we can cancel this delta theta throughout, and then we are going to introduce a definition here. We're going to say let tau equal the volume divided by the volumetric flow rate. So we can divide through by Q, and so we have here tau times I of theta is equal to, and this is a 1 minus, and this f of theta we can replace with this. So this is the integral naught to theta e of theta in theta. So this is a relationship now between I and E. This is the relationship we're looking for. So just writing it entirely in terms of I of theta, 1 over tau, 1 minus the integral naught to theta for E integrated in theta. And that's all there is to it, right? We know how to get this function E of theta, and this relationship is telling us that we just need to evaluate the integral from naught to theta on that function E of theta, take 1 minus the value that we get and divide that by tau, where tau is well defined. So if we just do that operation, then we can construct the function I of theta. So that actually closes the loop for us then, because we have an easy way to get E of theta, right? We said we can get it that way, and now we've got a relationship between E of theta and I of theta. So this operation is fairly easy to do, and this tau is a fairly practical variable. We can see there's nothing behind it than the volume of the reactor. So the volume, we do know that, and the flow rate, and we know that we must have set that as well. So that's That's not some weird abstract variable. That's simply the ratio of the volume to the flow rate, and it has a nice physical meaning, which we'll discuss now. So everything on the right hand side here is doable, and so we can get then 2I of theta. So that's how we can find the age distribution of any reactor. And you'll remember when we did the first video, we did not specify anything about the nature of the mixing here. This could have been a CSTR or a plug flow. I know it's not drawn that way, but we didn't say it couldn't be. Or it could be any real reactor. So it doesn't matter what type of mixing applies here. This relationship was derived without assuming anything about the mixing, so this must hold for any mixing pattern. And also here, we didn't specify anything about the mixing nature, right? This is the basic equation, and this says nothing about the mixing. So this is another general relationship that holds. So we can say then that it doesn't matter what type of mixing we have. We can use this relationship, we can perform the trace experiment, and we can get to E of theta. And the moment we have E of theta, we can apply this operation and we can get I of theta. And we're going to use this extensively now. Now, as promised, we want to comment on this tau value. So let's just think about the physical meaning of the tau value. So tau is the volume over the volumetric flow rate. And let's just apply some thinking to, let's say, a tubular reactor. So, oops. So let's say our volumetric flow rate here is Q and the volume there is V. And we know if that's the volumetric flow rate there, then we'll get that volumetric flow rate in here as well. And let's say the cross-sectional area here, AC, is constant. And let's define Z here. So Z is the axial position as we're looking down this tube. And let's divide both these quantities by Z. So we've got tau equals V over Q. And we can divide numerator and denominator by AC. So if we do that, the volume divided by the cross-sectional area, well, that must be the length here, so the length L. So that's L over, and then the volumetric flow rate divided by the cross-sectional area, that must be the linear velocity. So if you think about this, this is length over velocity, so that must be the time taken, right? The time taken by the fluid to get from this point to this point. Right. Once more, if you just think about even the most basic example, there's some distance L, and our stick figure here is running along at velocity u. Then the time taken to get from there to there must be the distance divided by the velocity. So that's what we have here. So tau is the time taken to get from here to here. In other words, it's the time that the fluid spends in that reactor. Now, that applies to the simple case where we have a fixed cross-sectional area. But the same concept applies to any reactor space. So if you have some kind of reactor space, doesn't matter what it is, and if we have a volumetric flow rate here and a volume there, then we could say that, well, the volume divided by the volumetric flow rate, that must be some indication of the average time that that fluid is going to spend in there. So tau is an indication of, on average, the time spent by the fluid in that space. So that's why it's called the space-time, right? Space-time, how much time do you spend in that space, right? It's a little bit confusing because today we often think about space-time continuum and all that, but that's not what that means. It's space-time, how much time do you spend in the space. And you see there's a nice quick easy way to figure that out. We just take the volume divided by the volumetric flow rate, and that's what it is. So this variable is not unfriendly. We have easy ways of estimating it, and then we know how to get E of theta. So I of theta, it's not a great stretch to work that one out.